Welcome back to ECE 501B. I guess they are paying attention to the videos maybe. I thought I heard a comment that the numbers just don't seem to add up in the classroom, but well, yes, I'm not sure how we want to interpret that, but one might be that it was a little bit stormy today. How's that? So maybe, yes, maybe they all got mapped to the null space, which is the zero vector. But you'll have the opportunity to work on some of these mapping issues in homework number 3, and that's due in a week. Our exam is due or will occur a week from Wednesday, and there is material on D2L relative to exam number 1, some practice exams, and even a review lecture from a previous semester. The notes for that and the video capture. Today what I want to do is talk about matrices and how you can build a matrix from these linear maps. We really haven't put a matrix or built a matrix out of these linear maps. We've just had a linear map T taking, let's say, XYZ into some other dimensional space, either R2 or R5, something like that. Let's now look at just this notion of building a matrix representation from a linear map. We'll look at several examples, and that's where I hope to get covered today. And if we get far enough, we will breeze through the matrix operations. I'm assuming you know how to add matrices. I'm assuming you know how to scale a matrix with a scalar or multiply a matrix by a scalar. Matrix multiplication, I think you sort of know the row column way of doing it. We will talk about another way of interpreting a multiplication of matrices, and also we'll talk just briefly about the matrix vector product. Then we will get into, this is sort of giving us a plan through or up to exam number 1. We will then get into invertible maps, and an invertible map is if and only if it's injective and surjective, or if and only if it's one-to-one and onto. That's an invertible map. We will talk about isomorphic vector spaces, which really means that these two vector spaces are similar. And then we will talk about operators, and then we'll spend most of the rest of the semester with operators, which really says that your domain and codomain vector space is the same. Yes? Yes. So the question was, injective is one-to-one and surjective onto. That's another way of making that connection or translation. Whenever you see injective, you could just say one-to-one. Or if you're seeing surjective written, you could think of as onto. Surjective is trying to cover your codomain. Injective now just means that you can really, you don't map many to one. You map one to one. The many to one would mean that you have a non-trivial null space. If you had many vectors going to the same one unique vector in the codomain. So we are thinking of a one-to-one map. Let's now talk about this idea of a matrix representation of a linear map. And let me write down what I hope to get covered today. Given a linear map, the notation is then we have this linear map T that's in this set of all linear maps from the domain V to the codomain W. And suppose that we have a set of basis vectors for the domain. That's now n vectors or Nevada vectors long as a list on the domain, and let's obtain then or identify and a basis W, which is, let's say, Michigan long on the codomain. We have a linear map mapping between these two sets of basis vectors. The action of the map on the kth basis vector which is v sub lowercase k, can be written as a linear combination of the basis vectors on the codomain. By that I'm meaning we have t operating on v sub k is now a sub 1 comma k w1 plus a sub 2 comma k. So I'm double subscripting. I shouldn't have used k. I can't do lowercase k's very well. Maybe I should have used an L, but those are supposed to be k's. A sub 2k, w sub 2, on up to a sub m k, w sub m. And that particular expansion, we can actually use these A's to fill up columns of a matrix. These coefficients in that top row that's identified on the screen right now, that's only for one basis vector, v sub k. We can do that for all n or all Nevada of those v vectors. These coefficients for all the Nevada vectors v sub k can be collected in the Michigan by Nevada matrix that I'm going to write now. That matrix now is a sub 1 comma 1, a sub 2 comma 1, down to a sub m comma 1. And those are the A's that are actually associated with the weighting of the codomain basis vectors corresponding to TV sub 1. That's that vector. TV sub 2 is now a sub 1 comma 2, a sub 2 comma 2, down to a sub m comma 2. That just keeps going, and we have our kth column that we identified before. And we keep going until we reach our nth mapping from the nth basis vector v sub n, which will now be a sub 1 comma n, a sub 2 comma n, all the way down to a sub m comma n, with the corresponding columns then being TV sub 1, TV sub 2, TV sub k, and TV sub n. And that's the matrix representation of this linear map T in terms of the n Nevada basis vectors in the domain v1 through v sub n, in terms of or mapping into a set of basis vectors in the codomain that we've labeled as w1 through w sub m. Let's look at an example just to put some flesh on this. Suppose that we have a linear map that's going to go from R3 to R2. And we've been calling that a dimension reduction map. We're going from three-dimensional space to a plane. And suppose that t, x, y, z is now 2x minus y plus 3z, and the second coordinate is 7x plus 5y minus 6z. In order to do this or create a matrix for this linear map, we have to now start with a basis for our domain space or vector space and a basis for our codomain or a vector space W. Suppose we pick for a basis for our domain the following. V1, let me make that 1, 0, 0. V sub 2 is 0, 1, 0, and V sub 3 is 0, 0, 1. And suppose that the basis for the codomain it's now two-dimensional. Let's say that W sub 1 is 1, 0, and W sub 2 is 0, 1. These two sets of bases should look very generic. They're called the standard basis. These bases are the standard basis, and typically if we don't mention a set of basis, we're implicitly assuming this kind of basis structure. Ones in each coordinate and zeros in every other coordinate. And we have V1 is 1 in X, V2 is 1 in Y, and V3 is 1 in Z. With that particular set, now let's create a matrix corresponding to these two sets of bases in R3 and R2. First, what happens when we use or apply the linear map on the first basis? V1 is just 1 in the X coordinate. TV1. Now if we go here and say, let me set Y and Z to 0 and X to 1, I obtain a two-dimensional vector 2, 7. TV1 is 2, 7, but how does that made from our basis vectors in the codomain? Well, that's actually 2 times W1 plus 7 times W2. It looks trivial, but this becomes a little bit more interesting or useful when we have the non-standard basis vectors being used. Or we could think of this, if you thought of W1 and W2 more as columns, 1, 0, and 0, 1, now you could build up this result, TV1, which would be 2, 7. Again, it's a two-dimensional space, and in fact, this 2, 7 column will be the first column by definition of how we did the matrix representation of the matrix representation. The 2 is what's weighting W1, and the 7 is what's weighting W2. And we can continue with this process to build the next two columns. To find TV sub 2, V sub 2 is only 1 in the y coordinate or in the second coordinate. TV sub 2, we go back to the linear map and we say, what does that become when y is 1 and x and z are both 0? We now just get minus 1, 5 for our vector in R2. So that now TV sub 2 is minus 1, 5, or that's minus 1 times 1, 0, plus 5 times 0, 1. Or that's minus 1 times W1 plus 5 times W2. Or if we do it again like we had done up above, we now have W1, which is this column, 1, 0. W sub 2 is the second column, 0, 1, stacked on top of each other. I can obtain TV sub 2 by scaling W1 by minus 1 and W sub 2 by 5. And this now becomes the second column, in the matrix representation. Completing that process, TV sub 3, now V sub 3 is 0, 0, 1. TV sub 3 will be what's left when we set z to 1 and x and y to 0. That becomes 3 and minus 6. Which is now 3 times 1, 0 plus minus 6 times 0, 1, which is 3W1 plus a minus 6 W sub 2, or we can now build TV sub 3 from a combination of W1 and W sub 2 by weighting that by 3 minus 6, and that now becomes T V sub 3. This is now the third column in our matrix, and we will now indicate that the matrix representation of the linear map T, that's supposed to be a script M with an argument of capital T for the linear map, is now the first column, 2, 7. The second column is minus 1, 5. And the third column is 3, minus 6. Where this is TV1 as a linear combination of W's. This is TV sub 2, and the third column is TV sub 3. That one seems trivial because of the way that we selected our basis vectors. The basis vectors were the standard basis. Let's make it a little bit more interesting with a different example. And in this example, I'm going to use 4 different sets of basis vectors. Here, let's look at a linear map. So now this is now a matrix representation T that's mapping from R2 back onto R2. But before we get too much into the matrix representation, let's just try to represent a single point in a 2-dimensional plane in terms of 2 different basis vectors, 2 sets of basis vectors. let's examine a point, which I'm going to call P sub 1. Using two different bases. For its representation. Let me see if I can draw this. Here's a plane, and the point P1 that I'm going to be working on is right there. Let me call that P1. And what I want to do now is let me pick the first set of basis vectors as my standard basis, meaning let me say it will be made up of V sub 1 and V sub 2. And the other set of basis vectors you can think of as related to V1 and V2 if you wanted to, but these particular basis vectors are going to be rotated, let's say counterclockwise 45 degrees from V1, V2, and they're going to be stretched. Meaning, let me make V1 bar that vector, which in the standard basis is 1, 1. We always sort of go back to our standard basis. And V2 bar is now minus 1, 1. Let me write those down. We now have two different basis vectors that we are going to use to represent the single point P sub 1. Basis vectors will actually change how the point P1 is represented by a vector. By that, I'm saying let's write P1 in terms of a linear combination of V1 and V2 and form a vector of those weightings. And then let's also represent P1 in terms of V1 bar and V2 as a linear combination of those two basis vectors. And those weightings we will also put into a vector. And the idea is we're going to get two different vectors that represent the same point. But it just means that we are using two different sets of basis vectors to represent that point P sub 1. For example, here, I'm going to go ahead and define capital V as this list of two vectors, V sub 1 as a column and V sub 2 as a column, and capital V bar is now V1 bar and V2 bar. Where this particular basis is our standard basis, and this basis, the barred basis, is actually rotated CCW or counterclockwise and actually stretched. They don't have a length of 1, they have a length of square root of 2, for example. Now let's represent P1 in terms of both of those basis vector sets. representing P1 in terms of, let's say, the V basis vectors, allows us to say we want V when now that capital V are the columns V1 and V2. We want to weight those by an A1 and A2. A1 will weight V1, A2 will weight lowercase v sub 2. If we write that out, we have 1, 0, and 0, 1, with this being V1 and this being V sub 2. We are now trying to find coefficients A sub 1 and A sub 2 that will weight those two basis vectors. Written out, we could say that that's A1 V1 plus A2 V2, or that's also A1 times 1, 0 plus A sub 2 times 0, 1. If that's the case, how are we going to represent P1 in terms of those two basis vectors? What are the values for A1 and A2 to get to that red point? We need each of those to be weighted by 1, don't we? We need A sub 1 to be 1 and A sub 2 to be 1. That gives us then our representation, let's say, of P sub 1 in the basis set V as A1, A sub 2. That's what I'm saying here. Let's now represent P1 in terms of the barred basis vectors. So that now we have V bar that's going to be weighted by A1 bar and A2 bar. Or we now have what was V1 bar as far as a column. So V1 bar in terms of, and this is maybe a little bit, do you see that it's just 1, 1? This is V1 bar. This is what gets maybe a little bit confusing. We're writing V1 bar sort of in our standard XY plane, but V1 bar is now found by taking 1 in the X and 1 in the Y, and that gets us to V1 bar. So we are going to, what we're trying to do is just, how do I want to say this? We want to create, I mean, if we didn't have to specify these with coordinates in vectors, we could just have these basis vectors identified graphically, and now we just paste them together or scale them to give us whatever point we want. But right now we need to sort of write these in terms of coordinates in vectors. V sub 1 bar we will represent as 1, 1. And what's the length of that? That's now 1 squared plus 1 squared, the Euclidean square rooted, or the square root of 2. And what's the angle? It's 45 degrees, if you wanted to think of it in terms of polar notation. What is v sub 2 bar as a vector? That has an x-coordinate of -1 and a y-coordinate of 1. So that down here, this is now -1, 1. We want to find then how to combine A1 bar, or how to combine V1 bar and V2 bar by the appropriate scalars, A1 bar and A2 bar, to produce the point P1. This is now A1 bar times V1 plus A sub 2 bar times V sub 2 bar. And now how do we weight those two vectors to get to the location in the xy plane 1, 1, which is P1? Is it clear that we don't need to have any weighting on the second basis vector? And we can take all of the first vector or scale it just by 1, which leaves us then with another way to write the point P1 in terms of the V bar basis. This now becomes 1, 0, which is A1 bar, A2 bar. The main thing that I'm trying to show in this first part of this exercise is that as a vector, if somebody just hands you a vector, it may not mean anything unless you know what those coordinates correspond to. In this case, they could say, okay, here's 1, 0, and that's equal to 1, 1. And you're going, what? Well, those are both representing this red point, P sub 1, just in terms of two different sets of basis vectors. That's all I'm saying. Now let's see what happens when we apply a linear map to P1, for example. Let's consider the following linear map. Suppose that T, and again, this linear map is from R2 to R2. Let's say that this now becomes 2x minus 1/2 y and x plus 2y. Or now we have T is a linear map from our domain R2 and our codomain onto our codomain R2 also. Now, suppose that we've already picked essentially two different sets of basis for R2, a V and a V bar. Let's use both of those to represent different basis on our domain. Now let's create two other bases in W for the codomain. Let's let W be W1 and W2, and that should look very familiar. That's just our standard basis again. And so we're going to map from V to W, and then we're going to map from V bar to a W bar, where now let's pick some basis vectors for W bar. So that now let's say it's 1 minus 1 and 1, 1. Where this is now W1 bar and W2 bar. And what have we done with this set of vectors for our basis? Now the first one, we go over 1 right and down 1 in the y direction, so that now W1 bar is that vector, and W sub 2 bar is that direction, or that vector. Again, this is rotated from our standard basis, but now it's rotated clockwise instead of counterclockwise. But again, it's also been stretched. So now the question was, do these basis vectors have to be orthogonal? And what does it require for a set of vectors to form a basis? They have to be linearly independent and they have to span the space. So no, they don't have to be orthogonal, although my choices are, so maybe that was a poor choice. But they are a set of basis vectors, aren't they? You can get to any point in the two-dimensional space by some linear combination of the W vectors or the W bar vectors. Likewise, the V bar and the V, those also span all of R2, and they are linear. They don't line on top of each other, so they're linearly independent. Is that okay? It just so happens that V and W are the same, but V bar and W bar are not the same. Now, what I want to do is I want to make or try to create a matrix representation of the linear map T between these different combinations of basis vectors. Or, what does T, the linear map, look like as a matrix? For A, where our domain and our codomain, let's say this is now V and this is W, and we now have this map T. We want to find the matrix representation of that linear map, and we want to do it for both. The other combination where our domain and codomain are V bar and W bar. Will the matrix representation be the same? I hope you can see that it's not going to be, but now let's build that up and see what these different matrix representations for this linear map are under these constraints, or with these sets of bases. The first one is what I'm calling case A. V was then 1, 0, 0, 1. Our codomain basis was 1, 0, 0, 1. These are all the standard basis for both the domain and the codomain. in this case, and in all cases actually that I've selected, the span of V is all of R2, which is the span of 1, 0, and 0, 1, or where we can get to by any linear combination of V1 and V2. And the span of W is also R2, which is the span of W1 and W2. And we want to know, what does the matrix look like in these two domain and codomain sets of bases for the linear map T, defined by 2x minus 1/2 y and x plus 2y. With that linear map, we can now look at T V1. That's now T evaluated at 1, 0. And now if we simply plug in 1 for x and 0 for y, we end up with 2, 1. And that now we want to write as a linear combination of vectors W1 and W2, which in this case look just like V1 and V2, so it maybe doesn't look very interesting, but I'm going to try to identify that. This is now W1 plus A sub 2, 1 W sub 2. Or you could say that's 1, 0, well, let me label it as W1 and W2. That's W times A11, A21. And we already know what that is. That's 2, 1 from up above. And we want that to equal some linear combination of these basis vectors, W1 and W2, which in this example, W1 and W2 are the identity matrix. We could invert the identity matrix if we wanted to, and now we have what those values for A11 and A21 are actually equal to. That's now 2, 1. And we could see that this 1 corresponds to the first basis vector of V. This 1 right there is the first basis in our codomain, or first basis vector of W, and this 2 is the second basis vector of W, is how to sort of infer these coefficients. A sub 2, 1 says, how do I weight the second basis vector in my codomain in order to produce this result 2, 1 that I'm looking for? Now we have the first column in our matrix representation. That's going to be 2, 1. Let's look now at T applied to V sub 2. Or if we go back to our linear map and replace x with 0 and y with 1, we end up with minus 1/2, 2. and we want that to be now A sub 1, 2, W1 plus A sub 2, 2, W sub 2. Or that's now W1, W sub 2 times A12, A22, the second subscript 2 corresponding to the second basis vector V sub 2. Again, W1 and W2 are the identity matrix. And we now see that we have A12 and A22 being minus 1/2 and 2. And if we wrote this out formally, we could say the matrix representation of the linear map T with a basis on our domain of V1, V2, and a set of basis vectors in the codomain W1 and W2, that will become our first column, which was 2, 1, right there. And the second column is this minus 1/2, 2. And maybe I'll call that A. That's now a 2 by 2 matrix. We were mapping from an R2 to R2. And now let's see if we had started with P1 in the V basis, capital V basis, we want to know how does that point or vector P1 get changed through this linear map that's now a matrix, capital A. What is going to be, let's say, Q sub 1 on the W basis? We're defining that to be this linear map now represented as a matrix, capital A, operating on P sub 1 in the V basis. We are trying to go from V to W, and we have two different basis sets. In this case, they're identical, but now we have A, and how do we write P sub 1 sub V in the V basis? How did we get to the point P sub 1? That was just 1 of V1 and 1 of V sub 2. In this case, now 1, 1, post multiplying this matrix A, you could view this as combining or adding those two columns. We have 2 minus 1/2 and we have 1 plus 2, or we now have 3/2 and 3 for our Q sub 1 on W. We're mapping now from the point 1, 1. This linear transformation takes us over a little bit in the X to 3/2, and it takes us quite a bit in the Y up to 3 from the initial starting point 1, 1. That's what the linear transformation did, and this is the matrix representation of that linear transformation in the standard basis set. Now we get to the more interesting case, which is case B. Where now what is the matrix representation of T when our basis for the domain is the V barred basis, and the basis in our codomain is the W barred. If we do the same process that we just followed, we want to know how do we, or where do we go, or how do we find the result of TV1 bar in terms of W1 bar and W2 bar. V1 bar was 1, 1. So that now we take 2 times x, which was 1, minus 1/2 times y, which was 1, x plus 2y, and that's actually what we just had for our earlier map, but this is now 3/2 and 3, coincidentally. We now want to write that as a linear combination of W1 bar. W1 bar was 1 minus 1, and W sub 2 bar was 1, 1. Or we now have A11 bar W1 bar plus A21 bar W2 bar. Or this is W1 bar W2 bar A11 bar A21 bar. If we plug these in, we have 1 minus 1, 1, 1, A11 bar, A21 bar is equal to, and we found that to be 3/2, 3. We want to know how to combine W1 bar and W2 bar by the choice of these scalars, A11 bar and A21 bar, to obtain 3/2, 3. And we can do this many different ways. Let's just do it as if we said, wait a minute, we have 2 equations in 2 unknowns. So let's do it the old-fashioned way. If we multiply this out, we see that we have A11 bar plus A21 bar equaling 3/2. That's the first equation. The second equation is minus A11 bar plus A21 bar, and that's equal to 3. That's kind of nice because now A11 bar is negated in the second equation. If we just add those 2 equations, we end up with 2. A21 bar is equal to 3/2 plus 3, or we now have 4.5, or 9/2. And this we can solve for A21 bar to find that's now 2 1/4, or 9/4. We can use that in one of those formulas. If we now solve for A11 bar, that's now 3/2 minus 9/4, or we have 6/4 minus 9/4, or minus 3/4. That's now how we would combine W1 bar and W2 bar in order to produce the point 1.5, 3. So that we now take minus 3/4 of A11 bar, or that's the scalar that we scale W1 bar with, and 9/4 to scale W2 bar. And this is the first column in the matrix representation of that linear map T. What about TV sub 2? V sub 2 was minus 1, 1. And we map that through the linear map T. We have 2 times x minus 1/2 times y. We have x plus 2 times y. Or we now have minus 2 minus 1/2, or minus 2.5 as the first coordinate, or minus 5/2. Minus 1 plus 2 is 1 for the second coordinate. We want to now find that in terms of W1 bar and W2 bar. This now becomes A12 bar W1 bar plus A sub 22 bar W sub 2 bar. Or A12 was weighting W1 bar, and W1 bar was 1 minus 1. And A sub 22 bar was 1, 1. Can I write that in terms of like a MATLAB notation? I now have the basis W, capital W bar, and I want to know what are my coefficients or scalars in the second column of my matrix representation, which I'm saying now is A colon means all of the rows, which I only have 2 of those, and I'm interested in the second column. Or this is now 1 minus 1, 1, 1 times A12 bar, A22 bar, and that's supposed to be minus 5/2 and 1. As I said before, 2 equations, 2 unknowns, we can solve it many different ways. Let's do it by inverting the matrix. So inverting a second order or a 2 by 2 matrix isn't too tough. I now have the determinant, which is the product of the diagonals minus the product of the off diagonals. And then I simply, now it even gets more confusing, but I interchange the diagonal entries, which were the same, so it doesn't look like I did anything, and I negate the signs of my off diagonal entries. My denominator is 1 minus a minus 1, or 2. And there's now the inverse of capital W bar. So that A12 bar, A22 bar, is now 1/2, 1, 1, minus 1, 1 times minus 5/2, 1. And now I scale the first column by minus 2.5, and I add in the second column. Or I'm taking away 1 from minus 5/2, and I'm adding 1 to minus 5/2. So that now I end up with minus 7/2 scaled by 1/2, or minus 7/4 in the first coordinate, and that's actually going to be my A12 bar. And my A22 bar becomes minus 3/2 scaled by 1/2, or minus 3/4. And this now becomes the second column in the matrix representation of T. So that now my matrix representation of T in this new pair of bases, the domain was V1 bar, V2 bar. The codomain was W1 bar, W2 bar. The first column was minus 3/4, 9/4. And the second column was minus 7/4, minus 3/4. And I hope that you can see that this is not the same as the matrix representation that we had before. We're going to call that now our A bar in the Bard notation. You can compare A bar with A, and they shouldn't look the same. 2 minus 1/2, 1, 2 is definitely not the same as minus 3/4, minus 7/4, 9/4, and minus 3/4. But if we apply A bar to the point P1 expressed in terms of the V bar basis and map P1 through this linear transformation, which now has this matrix representation, A bar, do we get the same Q1 point in two-dimensional space that we had using the earlier standard basis to use for our matrix representation? We're now trying to check our work. We're trying to see what happens when we take the point P1 in the V bar basis and map that into Q1 in the W bar, but now we are using the matrix representation of the linear map T in the V bar W bar basis. Let's see what happens. Now we have Q1 W bar should be A bar, which is minus 3/4, minus 7/4, 9/4, minus 3/4. And what was P1 in the V bar basis? Thought I had that somewhere. It's just 1, 0, isn't it? This is now P1 in the V bar. Good, I don't have to do too much math. This post-multiplying by a column 1, 0 is really just going to copy the first column of A bar, is another way of thinking of this multiplication. This is our A bar, and the product is now minus 3/4, 9/4. And what does that mean? Well, that means that we have minus 3/4 scaling what? This is supposed to be scaling W1 bar. And then we have 9/4 scaling W2 bar. Well, that now is minus 3/4 times W1 bar, which was 1 minus 1, plus 9/4 scaling W sub 2 bar, or that's now minus 3/4 and 3/4 plus 9/4 and 9/4, or we have 6/4 in the first coordinate and 12/4 in the second coordinate, and that's back where we wanted to be. That's now 3/2 and 3, so that now we have taken this point P1, which was starting right here, and through the mapping of A bar, we've now changed it up to 3/2 3, which is now Q1. And if you wanted to, you could now lay down these particular vectors, 1, -1, and say, oh, I want to move 3/4 in that direction, but then I'll back up that mirror image across the origin, meaning now I'm sort of saying, oh, where am I living here? Well, if I go 3/4 and then I back up, I'm sort of right there. This is now -3/4 W1 bar. And then I take 9/4 or 2 1/4 in the 1 1 direction. And the 1 1 direction, if I could sketch, that would go right through Q1, and I need to go up there 2 1/4. And that's where I get to, is right here. This is now 9/4 W2 bar. What can we take from this? A is not equal to A bar. It doesn't really matter what we have used for basis. The transformation will get us from any point to the other point using the same linear map. But it is important to keep track of which bases are being used for V and W. Thus, the matrix representation of T, let's say from V to W, on the basis V1, V2 up to V Nevada, and W1, W2, W up to Michigan, it's important to know what we're using on capital V and capital W, or on the domain and the codomain. And for that reason, the matrix representation of that linear map will be written as script M of T, V1, V2, V sub n, W1, W sub 2, W sub n. You may get writer's cramp. if you're having to write that all the time. And typically, if it's known what our basis vectors for V, capital V and capital W are, those get suppressed. Typically, they'll be the standard basis. When the choice of basis is obvious, then we will save our hand and we will shorten down the notation. Then we will use a simpler notation where it's just script M on T. Let me make an extremely important comment. As with vectors, and we've been using vectors all along until we jumped into chapter 3, and chapter 3 now we're using maps between vector spaces. As with vectors, maps have an existence separate from their matrix representation. And we saw that in the last example. Choosing different bases changes the values or the scalars in the matrix, and now think of the difference between A, capital A, and capital A bar in the matrix. But it still was able to get us from point P1 to point Q1, but does not change the truth or falsity of any statement about the map, nor any physically relevant numerical result. Now, as I said before, at the beginning of class, we were going to spend probably how much time on some of these matrix concepts? Half the semester learning how to do matrix addition? Probably not. How about 30 seconds in this lecture? So matrix addition, how is that done? Element-wise, right? But they have to be compatible matrices. You can't be adding a 2x1 to a 5x5 matrix. Matrix addition is element-wise. On matrices of the same size. and scalar multiplication simply scales all of the values in any matrix by the appropriate scalar. Scales values element-wise. So we will pick up at that point on Wednesday. I need to decide how much we will cover on matrix multiplication, but we will pick up with definitely isomorphic concepts and a little bit more of chapter 3. See you then.